Hello students, now we shall see this last part of this organometallic chemistry, that is catalytic property of organometallic compounds. Some organometallic compounds have transition metals with both saturated and unsaturated organic systems are of great utility as catalyst in organic chemistry and also in some industrial process. So some of these examples include Wilkinson catalyst, which is used in hydrogenation of olefins, HCO-CO4 in the hydroformylation of olefins, TiCl3, Al-C2H5 thrice in the polymerization of olefins, and so on. So what is the function of catalyst? So as we already know, catalyst speeds up the rate of reaction. So here also the working of the catalyst is as similar as the catalyst works in other type of reactions. A catalyst speeds up a reaction by replacing high energy barrier of an uncatalyzed process with a series of steps of much lower activation energy. So catalysts are of particular interest to industry because they speed up reactions as well as enabling them to occur with lower inputs of energy. That is both time and energy are since costly. By using catalyst, the reaction is speed up, rate of reaction gets speed up, and it becomes economical. Reactions will become some economically available. So how these are classified? So catalyst of general any organometallic compounds are classified into two types. One is heterogeneous catalyst, another one is homogeneous catalyst, or we call the heterogeneous catalysis homogeneous catalysis. Heterogeneous catalyst, that is catalyst and reactants are in different phase. 95% of all chemical and photochemical processes use heterogeneous catalysis or catalysts. Homogeneous catalysis means catalyst is in same phase as that of reactants, generally employed when selectivity is important and isolation of products from the reaction mixture can easily be activated. So that is how these two catalysts are used in case of organometallic reactions where we use organometallic compounds as catalysts. Then coming to the next part, that is Ziegler-Natta catalysis. So Ziegler-Natta is also a catalyst. So how the name came to this Ziegler-Natta we shall see now. So usually this is used in the polymerization of olefins, that is alkenes. A Ziegler-Natta catalyst is named after Carl Ziegler and Guido Natta. So these are two different scientists. So who worked on this organometallic compound, that is Ziegler-Natta catalyst, and they have been awarded Nobel Prize for this work also. So Ziegler-Natta catalyst, which is named after Carl Ziegler and Guido Natta, is a catalyst used in synthesis of polymers of 1-alkenes, that is we call it generally an alpha olefins. Again, in this Ziegler-Natta catalysis also there are two types. Two broad classes of Ziegler-Natta catalysts are employed, that is depending upon their solubility. One is heterogeneous supported catalysts and homogeneous supported catalysts. Heterogeneous supported catalysts based on titanium compounds are used in polymerization reaction in combination with co-catalysts. Organoaluminum compounds such as triethyl aluminum. This class of catalyst dominates the industry. That means in industrial purpose, most of the industries, this heterogeneous type of catalyst is generally used. Mm, it is used in polymerization reaction in combination with other catalysts. It is all most of them may be used as organoaluminum compounds. Homogeneous catalysts. Homogeneous catalysts are usually based on complexes of group 4 metals, that is titanium, zirconium or hafnium. They are usually used in combination with a different organoaluminum co-catalyst, methyl aluminooxane. These catalysts traditionally contain metallocenes but also feature multi-dentate oxygen and nitrogen based ligands. So this is about the classification of Ziegler-Natta catalyst. We shall see how it is employed in the reaction. So Ziegler-Natta catalysts are used to polymerize terminal alkenes, that is ethylene and alkenes with the vinyl double bond. So reaction is given NCH2 double bond CHR, which polymerizes and gives CH2CHRN. So general reaction of the Ziegler-Natta catalyst is with titanium tetrachloride reacts with triethyl aluminum, and this forms a Ziegler-Natta catalyst. A reaction between titanium tetrachloride and triethyl aluminum gives rise to an catalyst, that is we call it as a Ziegler-Natta catalyst. So when ethene is made to polymerize using this Ziegler-Natta catalyst, we get a polyethene. So there is very much difference between general polymerization and polymerization using Ziegler-Natta catalyst. See how it happens. We shall see this mechanism. So mechanism of Ziegler-Natta catalysis. So below in this structure you can see titanium is bonded to the octahedral chlorine atoms. So that means 6 chlorine atoms. Here we have given 5 chlorine atoms, and one is a square box we have given which indicates a vacant site. So titanium bonded to 5 chlorine atoms and one is vacant site. When this type of titanium chloride made to react with triethyl aluminum, there forms an Ziegler-Natta catalyst. So you can see the structure, what happens. So it gives rise to an that vacant site is made to fill with the triethyl aluminum. Triethyl aluminum. So triethyl aluminum, how it bonds to that vacant site? So it bonds through the ethyl group, and remaining at ethyl group again bonds to the diethyl aluminum. So again you can see this is present in the square bracket, that is an intermediate product. Again one more vacant site is created. One more vacant site is created in the next further reaction. Again this is made to react with the triethyl aluminum. So this reaction goes on adding up this triethyl aluminum to the vacant site of the uh, titanium tetrachloride, what we call, or titanium trichloride. See, most familiar example of Ziegler-Natta catalyst is one formed from titanium tetrachloride and aluminum triethyl aluminum. Why I am saying is titanium trichloride, one site is made vacant. If not, the formula would have become TiCl6. So that's how it formed. We shall see next. So this is active catalyst for the polymerization of ethylene, acting as heterogeneous catalyst. So this is, you should remember, the Ziegler-Natta catalyst is an heterogeneous catalyst. To understand how the catalyst works, you must look at the crystal structure of TiCl3. See, even though we are making to react with TiCl4 with triethyl aluminum, as I said, one in the reaction in the mechanism we have seen TiCl6, one site is vacant. In similar way, in TiCl4, one site is vacant, that's why we write it as TiCl3. In solid TiCl3, a titanium atom in the center of the crystal is surrounded octahedrally by 6 chlorine atoms. So this is what we have seen in this structure. Starting in the mechanism of Ziegler-Natta catalyst, there should have been 6 chlorine atoms, but instead there are 5 chlorine and one vacant site. Each chlorine atom is further bound to the titanium atom. So this is how you have to understand the structure of this TiCl3. It's not TiCl6, it is TiCl3. Since this is a huge structure of TiCl3, that is it is not a dimer or trimer, it is almost a polymer structure of TiCl3. Ti is bonded to 3 chlorine atoms. Each chlorine atom in turn is bonded to titanium atom. Again each titanium atom is bonded to the 3 chlorine atoms. So if each chlorine TiCl3, if each chlorine is bonded to 3 Ti titanium atom, then that titanium atom is each bonded to 3 means each bonded to 3. So totally it becomes again 9 chlorine atoms. So this is how we have to imagine the structure of TiCl3. However, if such bonding is carried on indefinitely, or just like infinity we can say, so it is apparent that in order to make the crystal electrically neutral, some of titanium atoms at the surface, that is at the edge or at the terminal, should have only 5 chlorine atoms around them and they possess a vacant site. So this is how we can understand why there is vacant site. That is, this structure goes on building TiCl3, TiCl3, TiCl3. This becomes a very huge structure, but at the surface, that surface means here terminal side of this structure, some site must have been vacant. So this vacant site is represented by a small square box. On treating such a crystal of TiCl3 with triethyl aluminium, this vacant site is alkylated. So this vacant site is alkylated. So you have to understand this vacant site, where there is vacant site present in the TiCl3, that site is filled by the alkyl group of the triethyl aluminium. One alkyl group attaches, so as we have seen already in the reaction, one alkyl group attaches and remaining diethyl aluminium attaches to this alkyl group. On treating such a crystal of TiCl3 with triethyl aluminium, this vacant site is alkylated. The starred chlorine indicates a chlorine bound to the second titanium atom, and an unsaturated chlorine atoms lie on the surface of the crystal. So if any chlorine atoms, if it is marked with a star, it indicates again more titanium atoms are attached to this chlorine atoms, which in turn each titanium is atom is attached to the 3 more chlorine atoms for each titanium. If there are 4, then it becomes 12. If there are 5, it becomes 15. So here we have given, so again 6 sites we have given. One site is already attached with the ethyl, one is, now the vacant site shifts. It doesn't mean if one vacant site is filled up by the ethyl, the polymerization doesn't get completed. It means the vacant site is created at the another part of the chlorine atom. When this type of structure, that is titanium with chlorine atoms, ethyl group and one vacant site, is made to react with the further one more alkene. Now this vacant site, so again gets attached to the alkene group, this alkene. So that is what we see in the alkylated product. The vacancy in the coordination shell of the titanium is still present, but in a fresh position, that is in the another position. This vacant site is potentially capable of coordinating an alkene such as C2H4. So this is what we have written on the arrow mark, H2C double bond CH2. The alkene coordinates to the titanium atom as a pi donor in its vacant coordinate site. The electropositive nature of titanium atom allows the electrons in the TiC2H5 bond to float towards the C2H5 group. When an alkene and an alkyl group are bound to the adjacent sites on the metal atom, they react to give what is known as insertion product through a concentrated 4-center rearrangement. So next step we can see titanium. Again we have 4 chlorine atoms, one is C2H5. The vacant site is filled with alkene. So this becomes another insertion product. So now here titanium has this third site is filled with again alkene. So this is what we call a rate determining step, because this is the slowest step, is always the rate determining step in any of the reaction where determine the rate of reaction. This step is assumed to be the rate determining step. The alkyl group shift to the 1 carbon of the alkene double bond. The alkyl group now shifts to the 1 carbon of the alkene double bond. This is what they have shown. The alkyl group which was present at the above, now their vacant site has been created and alkyl group shifts to the another, that is alkene group, 1 carbon of the alkene group. Now again this type of product where there is 4 chlorine atoms, one alkene group, one CH2 C2H5 and one vacant site. When this type of product is made to react with one more alkene, now how the product becomes, how this polymerization chain goes on building up, you can see there is again 4 chlorine atoms, one to the vacant site a alkene is attached and there is another alkene, this with a single bond and with C2H5. So the alkyl group shifts to the one carbon of the alkene double bond while the other carbon develops a sigma bond to the titanium atom. When the rearrangement of alkyl and alkene carbon is complete, a new coordination site is again opened up on the titanium atom, cis to the, that means cis means that is the cis position, cis to the new longer alkyl group. This regeneration of vacant site enables the process to be repeated, and this goes on repeated and there forms a polymer, that is we can call it as polyethylene. So as we have seen in the this structure, ethene using Ziegler-Natta catalyst it forms polyethylene. So that is how this polymerization occurs to form polyethylene from ethene using Ziegler-Natta catalysis. So right. So how this is useful? What is the importance of this Ziegler-Natta catalyst? One of the features of organometallic polymerization compared to the general polymerization catalyst is that they produce stereoregular polymers. In general, they just form a polymers. There is no separate type of any type of polymer is formed. A chain of monomer, maybe a straight chain or branched chain of monomer, giving rise to a polymer is found. But when by using Ziegler-Natta catalyst in this polymerization, stereoregular type of polymers are formed. For example, you can see propylene forms two stereoregular polymers, namely isotactic and syndiotactic polymers, and one non-regular polymer, namely atactic polymer. In isotactic polymer, the methyl group always lie on the same side of the chain. So this is how we can see a empty circle represents carbon, a circle with the filled shows methyl, and small circle which is dark side of the ring it shows hydrogen atom. In isotactic polymer, methyl group, that is uh, a circles, big circles which is filled, methyl group always lies on the same side of the chain. So here you can see in the second carbon atom, the left side is methyl, the right side is hydrogen atom. So all you can see left side for again for fourth carbon atom, left side is methyl, a dark circle, big circle and a small circle, and again sixth above there is a methyl group and hydrogen, and again eighth. So this is how it continues. So in isotactic polymer, methyl group always lie on the same side of the chain. So this is similar in case of in the same syndactic polymer also you can see methyl groups are arranged alternate along the chain. So here you can see again in the second polymer, second carbon atom it is again left side, in fourth carbon atom is it right side, in sixth again it is left side, in eighth it is again right side. So this is so on. This is in syndiotactic polymers, methyl groups alternate along the chain. Then coming to the non-regular type of polymer, atactic polymers. In atactic polymers, the methyl groups have no regularity along the chain. There is no regularity left along the chain. When double bond of propylene attaches itself to titanium, the methyl group must always point away from the surface of the crystal simply because reaction occurs on the surface. Thus, when the molecule migrates and is inserted into the titanium carbon bond, it always has the same orientation. This is called cis insertion of the alkene and explains why polymers produced are stereoregular. So that means when double bond of propylene attaches itself to titanium, The methyl group must always point away from the surface of the crystal because reaction occurs on the surface. So right, this is why you can understand why this stereoregular type of polymers have been formed from this propylene. So this is from the organometallic chemistry. So this completes all topics of organometallic chemistry. So next page I have given some questions from previous question papers, you can refer. So, and if you have any doubts regarding this chapter, you can message me. So there are some questions. So some have been, I have written R1 means it is repeated again one time in the papers. If it is a 2, it has been repeated twice. So this is some very important questions. They have given right structure of ferrocene. This is for 1 mark. This is a 2-mark question. So usually now we have 1 mark. When there was 2-mark questions, this question have arranged in the 2-mark question section A. 4-mark questions explain structure and bonding in ferrocene and explain EAN of 16 and 18 electron rule with examples. So this question has been repeated once. That means twice is arranged. In 6-mark question, again explain preparation, structure and bonding of metal carbonyls. So this is also a very important question, even though it has repeated once. So this makes very important question. Describe structure and bonding in metal carbonyls. So see, this is also a same question, only they have not asked a preparation. So that means this question is very important. Every year you can understand a question regarding this metal carbonyls is always present in the question paper. Okay, thank you. This completes organometallic chemistry.